Okay, we're going to be jumping into 1.3 radicals and rational exponents. I'm going to split this up into sort of three smaller videos. So if you look at 1, 2, and 3, the objectives there, we're going to look at radicals and evaluating roots, and then we'll get a little bit in some operations, addition, subtraction. Then the next video we'll do multiplication and division, and then the last one we'll do the last objective, which is just dealing with rational exponents. So we go back to exponents there, but it involves radicals kind of thing. So there's a huge relationship there. So let's go ahead and jump in and look at evaluating roots. Now, a lot of this information, again, you probably have seen before. We just want to make sure that there's some terminology here we want to utilize and be aware of if I say it in a lesson or on an assignment or exam. So as you look at something like this, what we have is we have this radical symbol. Okay, and so that's a radical symbol. And what it does is it allows us to find roots of a specific value. And so here, if we want to find roots of something, it's like, what are we finding roots of? And so what's inside of a radical is actually called the radicand. Okay. And so that may be a little bit new of a vocab word, but radicand. So when I use that word, it means whatever the quantity is that's inside of the radical, that's called the radicand. And then what's really important, I'd say of really radicand, sometimes I'll just say the stuff inside. But this one's going to be the big one for us as we are evaluating and doing some operations, and that is the index. So that tells us what type of radical we have or what type of root we're looking for. So is it a square root, a cube root, a fourth root, and such. So um, hopefully what you recall about this index is that when there isn't one there, so much like this example that we have right here, when the index is not there, it actually is there. And so if there's no number there, there's actually a 2 there. So we don't usually put the 2. It's like having a coefficient of 1. It's implied. Because we use square roots so much, they just said, well, quit just putting a 2. Because we use it so much, let's imply that it's there. So that's what we have. The first example is a square root. And what that means is we're trying to put things in groups of 2. So the index identifies what we're attempting to put factors of the radicand in groups of. Okay, so sometimes the analogy I use is I use the radical symbol as like the house. Okay, so there's an inside and then there's an outside of the house. And so, especially at this time, we definitely want to occasionally go outside of the house. But like most parents, they won't let youngins go outside of the house without being in a group. And so the index is like the flag that's on our house, and that indicates sort of how many factors need to be in a group. In other words, how big of a group do you need to be in order for you to leave? If you can't make that number, then you can't leave the house, kind of thing. And then you leave as one full group. Okay, so keep that in mind. Sometimes I use the house analogy when I do these. So the second example here is a cube root. And so what that means is I would end up prime factoring down the radicand, see what it's made up of, and I'm looking for sets of 3 of something. So 3 2s or 3 3s or 3 5s, whatever it may be. I'm looking for a set of 3 in order to take as many groups out as I can. So that's sort of the point. Now, when we take, when I say something like the square root of 25, I'd say most of you would say 5 is your answer. And what you just gave me is what's called the principal root. So the principal root is really just the positive root. And that's what most of us are going to do. And so don't change anything there. There just is a name for it. If I wanted the negative root, because technically there's a negative root of the square root of 25, because by definition, the square root of 25 is simply saying what squared gives me 25. Well, think about it. 5 squared gives you 25. So that means 5 must be a root. But wouldn't you also agree that negative 5 squared is also 25? So you can also say negative 5 is also a root of 25. So if I say the square root, so how do we put in that we want a negative root? Okay, how do I notify you that this is what I want? So a negative root is when there's simply a negative out in front of a radical. Now, most students won't look at that as maybe a negative root and just look at it as a negative, like, oh, it's the negative of whatever I get inside. And that's perfectly fine. There's nothing wrong with that. So I wanted to make sure at least we talked about those things before we go in. Okay, now a couple of things here that we want to make sure that we get down. Just sort of, this is sort of the understanding of radicals. So, do we really understand what's going on and what can be inside and what kind of answers do we get? So, if the index is even, so we're looking at a 2, 4, 6, 8, those kind of things as my index. The first thing is that the inside, the radicand must be positive. Okay, and if it is positive, then I'm going to get a real rational solution, or at least a real solution. It doesn't have to be rational. If the inside's a perfect square, it'll be rational. Okay, but it could be irrational if the inside's not a perfect square. If the and this is going to be positive, so I should put a positive real solution. If the index is odd, 3, 5, 7, 9, and such, and the inside is positive, so like the cube root of 15, the cube root of 27, something like that, then what we're going to get is we're going to get a positive real root for that one as well. Okay? So I'm talking mainly principal roots here. If the radicand is negative, so in other words, if I took the square root of a negative, again, you probably already know what this is. Now, I'm going to put not real. So the square root of a negative is not real because by definition, what squared gives you a negative? Well, but I hope some of you recall because you've already been exposed to this idea of imaginary numbers. And so really what this is imaginary. So it's not real. It would produce an imaginary solution of some sort of complex number. So radicand is less than, let's say it's less than 0. Then what we're talking about is negative on this one. I wonder if I have the 0 up here. Oh, there it is. Let me edit that. Oop, wrong one. I was wondering what in the world's going on there. There we go. Okay, so if the radicand is less than 0, so it's negative, but we're talking about an odd. So the cube root, the fifth root, the seventh root of a negative, that simply means you get a negative real solution. And so that works out. The cube root of a negative simply means your answer's negative. The square root of a negative means you take your eye out because we're talking imaginary. Very different. If the radicand is 0, what's inside, then what you get is you just get a real as well. Okay, it's neither positive or negative because it's 0. Okay? And so you sort of just get 0. Square root of 0 is 0. Now there's a relationship between radicals and exponents, and that is that they are inverses of each other. So they undo each other. And this probably makes a lot of sense because if you want to undo a square, you square root it. And if you want to do a square root, you square it. And so that's when we say inverses. Hopefully from our properties, we remember a little bit of this idea of undo. And so keep that in mind, as especially when we get to like solving equations and things like that, because we want to pull and peel some of these radicals off or some of these exponents off. And this idea of them being inverses may help. Now, real quick review on factorization. What factors are, it makes up a value. And so its factors are, they are multiplied to create a value. That's an R. Or okay, so when we talk about factors with the numerical values, what we say is what it's made up of, in other words. So in other words, what numbers does 25, what is it made up of? Well, 5 times 5. So what we say is 5 and 5 are factors. 32, what we have is if we go and we do prime factorization, let's say 2 and 16, and 2 and 8, and what you'll find about 8s is it always goes to 3 2. So I might as well just go there now. And so 32 is made up of 5 2's. So this is called prime factorization. When we talk about variables, the exponent sort of tells us what it's made up of. We have 3 x's, and then we've got 2 y's. And so that's the long way of writing it out. So the variables are a little easier because of the exponents. Okay, now why we're doing that is we may have to simplify these radicals through taking groups out. So I want to go ahead and share with you all 4 conditions that need to be met in order for a radical to be simplified. So this is a little bit like the Family Feud where there's 4 things that you've got to identify. The first thing is, get rid of that. So the first one that we're looking at is all the radicands. So in other words, the groups need to be removed. And so the radicand contains no groups of factors, so we need to remove the groups. So we're going to be doing that right now. Just to show you the other three, may not address all of them in this video, but in videos to come. No fractions inside of a radical. We use the quotient property of radicals to fix that. It's just split it up, in other words. So that one we can fix. Groups we can fix. No radicals in the denominator. And we can fix that as well. That's through this process called rationalization. So we're going to rationalize the denominator. We're also going to look at rationalizing numerator. So remember, rationalization isn't just used to simplify expressions because there's a radical in the denominator. It may be used to simplify expressions where there's a radical in the numerator. And so keep in mind, there's going to be some of those. And then the last thing, sort of the one that is the least visible for students, and that is the index needs to be as small as possible. So we'll look at that one at the very end. So let's talk about taking groups out. So when we get a radical like this, what we want to do is identify what our index is. And so in this first case, there's no number here, which implies that it's a 2. So what I have is the square root of 25. Now you know this, just it's 5, but I want to show you why it's 5. If we break down, then what I have is a group of 5s. Remember, for you to be able to leave the radical home, it has to be in a group of that many. And so I can take one group of 5 out. So whatever I take out, one group of 5. If you took 2 5s out, it'd be 5 squared because it'd be 2 groups of 5. Looking at the 6 through to 729. So this one maybe not as easy, we know in our heads as much, but if we break it down, we can go 9 and 81. I have a feeling we're going to have a lot of 3s here, so let's see. And you can see we're going to have a whole bunch of 3s. And we get here and we have 1, 2, 3, 4, 5, 6. So if you notice, our index is a 6, so we have to have 6 of something to make a group, and we do. And we have nothing else left behind, okay? So at this point, I have one group of 3, okay? And again, you don't need to put the 1 there, but I'm taking one group of 3 out. So the 6 through to 729 is 3. And to check yourself, all you got to do is take whatever you took out, so in this case 3, and then raise it to the power of the index. So if that's a 6, raise it to the 6th power, and you should get the radicand at that point. Okay, so that's a nice way to check yourself if you want to. Dealing with variables, we look here, and remember the exponents tell me how many I have, so I don't have to break them down and circle them. My index for this problem is a 2. So all I have is 4 x's, and I'm putting them in groups of 2. So I'm going to do the x's long ways, and then we'll do the y's a little quicker. Okay, but if I have 4 x's and I'm putting in groups of 2, that looks like what I can do is make 2 groups of x's. So I can take x, and then my 2 groups means x squared. Now, another way of doing that is simply through division. Instead of writing them all out, I could have taken my exponent and divided by my index, because that's what division is putting things in groups. So if I have 8 y's and I'm putting them in groups of 2, I should have 4 y's in each group with no remainders. And so everything works out really nice on those problems. Let's look at some that maybe don't work out quite as much. So we want to remove as many groups as we can. So we break 72 down to 9 and 8. 9 breaks down to 3 and 3. And 8, you'll see 8's a lot, so I tend to just go ahead and go straight to the 3 2's. Okay. Then we're putting things in groups of 2. So there's one set that I can take out. So I can take a 3 out. And I can take a 2 out. Pen doesn't seem to be working. There we go. So I can take a 3 and a 2, but the lonely 2 here doesn't have a friend to leave the home with, isn't in a group, must stay behind. And so inside of my radical, I still have that 2. Now, if there was something else left inside the radical, let's say there was a 3 still left inside the radical, then I have a 2 times 3 or a 6 left inside. So whatever we take out, we multiply. Whatever we leave in, we multiply. So what our final answer to this is 6 square root of 2. And that makes sense. I could have broken this down to 36 and 2, and 30 square root of 36 is 6, and then 2 stays inside. Okay, again, work these, pause the video, see what you get. I'm going to go ahead and go through this one as well. So this one goes to, let's say, 8 and 3. And again, I know 8 goes to 3 2's. And so that's where I'm at right now. I can take 1 2 out, but I left a 2 and a 3 behind. So I can take that lonely 2 or that group of 2 out, but I left that lonely 2 and that 3 inside, which means I left a 6. Now notice the third example, it's a cube root, so I'm putting things in groups of 3 instead of groups of 2. So in this case, 54, what we have is like 9 and 6, and then 9 breaks down to 3 and 3, and 6 breaks down to 3 and 2. And I'm looking for a set of 3 of anything. And so in this case, I do have a set of 3. I have a set of 3s. Then I have a 2 left behind. Now, this is what I see from students, okay? And it's incorrect. And so there's little things here or there that'll trip you up if you're not careful. So I'm hoping you can identify what's wrong with this. And the key on this one is my index should not change. A square root and a cube root are very different. And so we don't want to forget that there's an index there that we may be utilizing. Now, there's a huge concept, and so this is why I have sort of the cartoon character rubbing its hands sort of evilly. There's something that's really pretty intense here. We're getting real deep into radicals a little bit, and that is if I go from, and it only goes when the index is even. So when the index is odd, I call those big hippies because anything goes. So in other words, the cube root of a negative simply means your answer is negative. My answer can be negative, the inside can be negative. But when the index is even, we do need to be careful here because the inside cannot be negative and the outside is not going to be negative when I'm done because the square root of a positive is positive, the square root of negative is not real. So there is no chance to get a negative unless there's a negative out front already. So what we want to make sure to do here is anytime we go from an even exponent inside the radical to an odd exponent outside the radical, you must put absolute values around the base that went even to odd. Okay, now that's me saying it doesn't make a lot of sense. But when I have, let's say, a variable where I'm not sure what the value is, but I do know that the square root of it. So in other words, the result of this, whatever my answer is to this, has to be positive. Has to be. Because I have an even index, and the result of an even index has to be positive. So whatever answer I get better be positive, okay? All right, so I hope you agree with me. Right now, I have no idea what x is. So x could be positive, x could be negative. Can't tell, have no idea. So we have to assume it could be either one. Now, what we have is a square root and squares undo each other, okay? And so I'm left with is just x. Or you have two x's, you can take a group out, and then you have nothing behind. So whatever my answer is x. But remember what we just said. We just said we have to assume x could be positive or negative. And so if by chance x was negative, this is a contradiction. How can a positive equal a negative? So I have to guarantee that this value is positive, and the sort of symbols that we use to guarantee positivity, or at least non-negative, is absolute value signs. So I went from an even exponent inside. Now again, this only works for an even index. Odd index, it's a big hippie, anything goes. Okay, no problem. Don't need to worry about it. Even index, slow down, check it. If you go from an even exponent inside the radical to an odd exponent outside the radical, you must put absolute values around it. That also holds true as if you don't know what x is and it ends up being like even odd inside the radical, because I can't take the square root of a negative. So you might even see absolute values being inside of a radical as well. Now that's really rare. We don't do a lot with those, but we definitely do quite a bit here. So let's look at some. Okay, so let's do some numerical ones and some variable ones, and then we'll go to the addition and subtraction and roll on. So simplify the inside, then evaluate. Okay, when you get a problem like this, I have no problem with students going, oh, the square root and the squares cancel, and so I'm left with -3. But notice what you're saying. This is where our understanding of a radical, we lose our understanding. This is a square root. Index is a 2. The result of a square root cannot be negative. So in other words, you put a statement here that is false. That is not, the answer is not -3. So you're like, well, okay, well, if it's not -3, what is it? Notice we started with an even exponent inside, and now my exponent is odd. Anytime you go even to odd, you must put absolute values around that quantity, which makes it +3. Okay. Now let me show you an easier way to do this. If I'm just working with numbers like this, I'm just going to go ahead and simplify. -3 times -3 is 9, and the square root of 9 is 3. So I get the right answer. So my suggestion is to simplify the inside as far as you can, and then look at it. Same on this one right here. We got to watch our order of operations, but I'm going to go ahead and square the -3 first, which makes a +9, and then I have the negative outside. So now I'm taking the square root of a negative, and the square root of a negative is not real. Right now, you can put not real. I'm good with that. Eventually, what we'll do is the answer is going to be 3i. And if you put 3i now, I'm okay with it as well because you've already learned it type of thing. So either one, but right now, we're not going to talk imaginaries. That'll be down the road a little bit when we get to the complex numbers and stuff, but you can put it since you already know it. Same thing over here. This would not be real, so not real would be appropriate. Or if you do remember a little bit of your complex imaginaries, then you could put, in this case, this 5i. Let me rewrite that 5 a little bit. Looking at some of the bottom ones with variables. Now, this is where probably we want to make sure be very careful because we do get a lot of even odds on variables. Now, we've looked at the first one already, and so the square root and the squares are going to cancel in this case. Remember, you cannot take an exponent across a plus or minus sign. We'll look at that actually down on this one down the bottom. And a radical is an exponent, so you cannot take an exponent across a plus or minus sign either. So in other words, I mean this. If you have the square root of x squared plus y squared, you can't just get y plus x. You can't take a radical across the plus or minus sign. With exponents, you owe me soft snickerdoodles when you do that. Here, I think you would owe me some cheesecake of some sort. So please don't do that. We'll avoid those radicals across plus or minus signs. But here we got x. And again, you got to ask yourself, especially when the index is even. So here are 2. Did I go from an even exponent to an odd? And hopefully you answered yes. And that means for that base only, put absolute values around it. And the reason I say that base only is you look at the second example. Let's just start with the 16 and break it down. So as soon as I go to 4 and 4, there's my group. You don't need to go to all the way down to your primes. It's fine if you do, but in this case, I can stop there and I can take a 4 out. So I definitely can take a 4 out. I have 2 x's, and I'm putting them in groups of 2. So that means I can have one full group. And then I have 8 y's, and I'm taking 2 of them out. That means I have 4 groups, and I have nothing left over in the radical. So there's nothing left over. Now, my question is, did I ever go from an even exponent, not an even number or something like that, an even exponent to an odd exponent? Well, here I went 8 to 4. I'm good there. But here I went 2 to 1. So just around the x is all I need. If you put around the x and the y, you're being redundant because y to the 4th is positive because of the even exponent. On the very bottom one, students struggle with this one a little bit because they think they have to expand this. But notice all this is something raised to the 6th power. It doesn't matter. This is the base then. What I have in blue is the base. So I have 6 of these bubbles, and I'm putting them in groups of 2, which means I should have 3 full groups of that bubble that I can take out. Now, what's in the bubble is the y squared plus 3y. Okay, so I don't do anything, and I can't take an exponent across a plus or minus sign, so help you God, you would owe me soft snickerdoodles. But here I got to look and say I went from an even 6 to an odd 3. So I went from an even exponent to an odd exponent. Don't forget to put your absolute values around the base and exponent. That went even odd. All right. Let's look at some where there's some leftovers. Okay, so we're going to have some that are left over now. And so we take out as much as we can, leave behind what we can't. So I got 2. I'm going to go a little quicker on these now, but 2 divided by 2 is one full group with nothing left over, so no remainder. 3 divided by 2. You can probably do it in your head, but 3 divided by 2 is one full y, but with one y left over. So the remainder tells me how many y's I have left inside the radical. The quotient tells me how many y's I can take out. Okay, I will look at my index. It stays the same. I looked, did I go even to odd? Definitely the y's, no problem, but the x's, I did go even to odd, so I need absolute values. Looking at this next one here, I have 10 divided by 2, which is 5. 17 divided by 2, well, 17 divided by 2 is going to be 6, but isn't there a leftover? So we have a 1 leftover y. 21 divided by 2 is 10, but with 1 left over. And so that's where we're looking. And then I go, is my index the same? Yes. And then how about, did I go even to odd? Well, the only one that could have gone even to odd is x, and we went 10 to 5, so that's even to odd absolute value. So you see there's a lot of things going on. Don't go so fast that you forget about the absolute values. Looking at a cube root. Now, first off, the cube root, I don't need to worry about absolute values, anything like that. So it's a big hippie, anything goes. So I do 7 divided by 3, which is 2, but I do have 1 left over. And then 11 divided by 3 is 3 with 2 left over. So 11 divided by 3 has a remainder of 2. And then again, you want to be very careful. Does my index match up from the start to the end? So make sure to have that. I don't need to worry about absolute values because it's an odd index. Looking at the bottom ones, so a combination of both numbers and variables in this case. So if we look at 40, I can break it down. I'm going to go 4 and 10. 10 actually just goes to 2 and 5. So there's not a whole lot there, but 4 goes down to 2 2s. So I can definitely take a 2 out. And I left a 10 behind. I'm going to run out of room here. So let's do my best here to squeeze it in. And so we'll have a 10 left, skinny 10. A's, I can take, if they're put them in groups of 2, I have enough for one group, but I have 1 left over, couldn't leave the house. B's, I have enough for 2 B's, and there's no B's left over. I check my index, it stays the same. Did I go even to odd? No, I went even to even, and I went odd to odd, doesn't matter. Boom, there's my answer. Looking at the last one here, 56, it's 7 and 8. And remember, we said there's a lot of 8s, so this goes to 3 2s. So it looks like I can take a 2 out. Now there's already a 3 there, so make sure we understand we're multiplying any factors that are out in front or any factors that are inside. And then I left a 7 behind. And so I need my cube root, and I left that 7 behind. Okay, then I look at my y's. I got 6 divided by 3, which is 2, no remainders, and 3 divided by 3, which is 1, z, and no remainders. And this is a cube root, so I don't need to worry about absolute values. Okay. Last thing for this video is adding and subtracting radicals. You can only add and subtract radicals when you have what we call like radical terms. So what that means is you have the same index. So cube roots and square roots cannot be added or subtracted, and the same radicands. Now you'll hear me say a lot like the same last name. So the coefficient's like the first name. So like 2, and the last name is like the item name. So 4th root of 3a. So I have 2 of these things called 4th root of 3a. So we have first name, last name. The last name is the item. The first name is how many we have. So you can see that the variable factors, anything that we consider a variable factor, would be considered sort of the item's name. And the numerical factor is going to be how many we have of that. So we have 2 bananas and 5 bananas. And so if we added it, we'd have 7 bananas. See how the last name doesn't change? Kind of thing. Or if we subtracted, it'd be -3 bananas. Last name doesn't change. Some unlike radicals are this. You have same radicand, but different indices. Can't add or subtract those. Looking at one like this one, same index, different radicand, we cannot add or subtract those. Now, we can multiply these two, and we can actually multiply those two. It looks a little weird, but we'll learn a technique we can do that. But you cannot add or subtract them. They have to be exactly the same. So the process looks like this. Now, right now, we can't do anything because the radicands aren't the same. So it looks like this is sort of stuck. It is not the square root of 10, okay? If it was that easy, grade school kids could do it. So it's got to be a little harder than that. So we're going to break down 8 and see what it's made up of. And so it's made up of 3 2s. So it looks like I can take a 2 out. So the process is simplify all the radicals as much as you can, and then look for like radical terms. So I have 2 square roots of 2. And then I have a 1 in front of this, so 1 square roots of 2. So if you have 2 bananas plus 1 banana, you should have 3 n square roots of 2 bananas. Last name doesn't change. Okay. Looking at the next example, same thing. Just break it down. In this case, what you can break this down to is 4 and 3. 4 goes to 2, 2, so I can take a 2 out. And so I already have a 2 there, so multiply them, and I left a 3 behind. 27 breaks down to 9 and 3. 9 breaks down to 2 3s. So I can take a 3 out. I already have a 3 there, so remember to multiply those. Now look at our radicals. That's good. That's what we want. And we can do 4 and 12. I'm just going to break 12 down to 4 and 3, so I can just take a 4 out. And I already have a 2 there, so that means I have an 8, and then square roots of 3. So all of these are like terms now. If for some reason, let's say the last one was 13, you could only subtract the first 2 and then leave it as something, like -5 square roots of 3 plus 8 square roots of 13. So that's as far as you can go. But in this case, all of them are the same. So we look at the first names. That tells me how many I have. I have 4. I get rid of 9, which means I'm in the whole 5. And then I add 8, which means I'm out of the whole 3. So I have 3 of these items. So if you have 4 bananas, you take away 9 bananas. I don't know how that works, but you have -5 bananas. And then you would add 8 bananas. You're at 3 bananas. Okay. Last examples we have will look like this. And so here I can't do anything yet, but if I break down the square root of 12, it goes to 3 and 4, and then 2 and 2. And so what we end up getting is 7 square roots of 3 plus 2 square roots of 3. Look at that. Same first name, which means these numerical values can be added. Last name doesn't change. And then we get there. Looking at the next one, X sort of stays, but 25. Now 25 goes to 25, or excuse me, 50 goes to 25 and 2. And 25, we know what the square root of 25 is. It's 5. So we're going to pull that 5 out. Now there's already a 4 there. So we're going to have 20. And then they had that lonely 2 and that lonely X staying inside. Looking at 32, you can go, I'm going to go 16 and 2 because I know what the square root of 16 is. It's 4. So I'm going to take a 4 out. Now there's already a 6 there, so we're going to have 24, multiply them. And then I left behind a 2 and an X. And look at the last names here, the variable factors. Okay. So if the variable factors match up, then the coefficient or the numerical factors, we can go ahead and add or subtract. Last name or the variable factor does not change. Looking at the last one here, I'm going to go 9 and 2. Square root of 9 is 3. So I can take a 3 out, which means I have 9 square roots of 2. 50 we just did up here, so I'm not going to break it down again. I can take a 5 out, and we have 25. And then I left behind, in this case, square root of 2. And it looks like they have the same last names, so I have 34 of those items, and the item's name is the square root of 2. Okay, and there we go. And that's going to be what you do for lesson 1. And again, the next lesson is going to be multiplying and division, and then we'll work into the rational exponents at the very end.